Okay, so many people think of a base as the number of digits we use to count. For example, in our base 10, well, we have 10 symbols, right? We have these 10 symbols 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's it. We can count forever with these 10 symbols. Okay, but instead, we can think of a base in the following way. If we let x be any number, then a particular number is written in base x if it is equal to the sum of the products of its digits going from right to left with increasing powers of x. So an example in our base 10 would be, well, here, the number 5,417, that's equal to 5 times 10 to the third power plus 4 times 10 squared plus 1 times 10, or times 10 to the first, plus 7 times 10 to the 0, because anything to the 0 power is just 1. So plus 7 times 1. Okay, so there we know how to write numbers in base 10. But if we look at maybe a base 8 example, how about we had 2516? Well, if this is a number written in base 8, then this is going to be equal to 2 times 8 to the, again, 0, 1, 2, 3, so 8 to the third power, plus we have 5, then we have 8 squared, or plus 5 times 8 squared, plus 1 times 8 to the first, plus 6 times, again, well, times 1, but you can write that as plus 6 times 8 to the 0 power. And, right? Yes, right? That is true. Okay, how about, so we can do that in any base, right? That's true in binary, base 2, base 3, base 4, it doesn't matter. But can we have a fractional base? So, and a lot of these bases, typically we do use how many digits we have. Like in base 10, for example, we have 10 digits, 0 to 9. In base 8, yes, we do have 8 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8. But how about we have a fractional base? Let's say base 3 halves. Now, base 3 halves is base 1.5, right? Well, but in base 3 halves, we could use a 3 to 2 machine if we were using exploding dots, but we would actually be using the digits 0, 1, and 2. Now, 2 in this case is actually greater than the base. But again, using our definition now of a base, again, a particular number written in base is written in base x if it is equal to the sum of the products of its digits, going from right to left, with increasing powers of x. So for base 3 halves, a base 3 halves example could be, how about 2, 1, 0, 1? So if this is a number in base 3 halves, then this should be equal to 2 times, well, times 3 halves, again, we're into the, 0, 1, 2, 3. So 4 spots in, that'll be 3 halves to the third power. And then we have plus 1 times what? Times 3 halves squared. And then we have plus 0. Well, plus 0 times 3 halves, that's just plus 0. And then plus 1 times, well, 3 halves to the 0, which is just plus 1. Or plus 1 times, if you want, plus 3 halves to the 0. So is this true? Well, is this true? And if it is true, then what number is this? Right? This should be a number that we should be to convert to base 10. Is this true? So let's go ahead and try to compute this. So what would we have? Well, if this is true, then we would have that 2101 written in base 3 halves would be equal to what? It would be equal to 2 times 3 halves cubed. Well, 3 halves cubed, that's 3 cubed over 2 cubed. So that would be 27 over 8 times 2. So we'd have 2 times 27 over 8. And then we'd have plus 1 times 3 halves squared. Well, 3 halves squared is 9/4. So we'd have plus 9/4. And then we'd have, well, plus 0. So it's plus 0. And then plus 1 times 3 halves to the 0, which is just plus 1, right? Because 3 halves to the 0 is 1. Anything to the 0 power is 1. So we just have plus 1. All right. Can we work this out? Well, we have 2 times 27/8. So that's 2 times 27, which is 54. So this is going to be equal to 54 over 8. 54/8 plus 9/4 plus 1. But I guess we're going to need to get a common denominator here of, let's just write it out here, plus 9/4 plus 1. But then to add these fractions, we're going to need a common denominator, I guess, of 8. So, okay, so this is going to be equal to 54/8 plus, well, 9/4 multiplied by 2 over 2, we get 9 times 2 is 18. So we get plus 18/8. And then 1, of course, is 8/8. So plus 8/8. Okay, and what do we have? 54 plus 18 plus 8. That is 50, 60, 68, 69, 70, 71, 72. Plus 8 is 80. So this is going to be equal to 80 over 8. Oh, 80 over 8 is just equal to 10. This is just equal to 10. So the whole number 10 can be represented as a power of 3 halves, and we can actually see this if we go ahead and use a 3-to-2 machine. If we use exploding dots, we could see this if we just put in 10 dots. This would be a 3-to-2 machine. Go ahead and put in 10 dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And do the rule here. Says whenever you have 3 dots in any box, they explode and become 2 dots, 1 space to the left. So go ahead, do your explosions, and you should come out with the code for 10 as 2101. And that means that we can represent 10, right, as just a sum of products of powers of 3 halves. So this crazy, right, these crazy fractions, 54/8 plus 9/4 plus 1 turns out to be equal to just the whole number 10. Pretty cool. So yes, we can have fractional bases where we actually use more digits than the base. So a little bit, some people might object to that, saying, that's not the definition of a base, but I think it is. I mean, you can definitely see these fractional bases and again, I think the 3-to-2 machine shows that you can put in any amount of dots you want, and you will end up with a code for that number. So every number has a distinct code in base 3 halves or base 1.5. So it certainly is a valid number base. Pretty cool. See you soon.